simulation to show you. I've put a link of this on the course website. Okay. And what's really neat about this is, I'm pretty sure that this is LabVIEW. And this basically is doing this, particle in a box with some slight tunneling simulation for us. And so I'm going to go ahead and run play. So this is going to show us the time dependent. And so now I'm only looking at the probability density. But when I put on the wave function, and I've also told it to show me the real part and the imaginary part, I can see how the wave function is evolving in time. Okay, this white part, magnitude, that's more or less showing me the psi squared, the probability density. And what's also cool is each one of these correspond to different energy levels. So there I can pick psi 2. So this would be the first excited state rather. So I can go and pick psi 3, and you notice they look kind of like what we expect. But what I want to show you, so in this model here, let's just look at the probability density, okay? What I want to show you is I've got a really cool way of demonstrating how there is just a little bit of tunneling at the edge of these borders, okay? And it's really difficult to see, but I can change the width of this well on this simulation. And notice here when it's a really narrow width, only 0.2 nanometers, there's only predicted to be 2 bound states that can fit in there. And look at this crazy, insane amount of tunneling that can happen there, right? So if you look at the purple line, if I widen that out, and of course, as you can see, as I'm widening it out, I'm getting more bound states, right? So I'm going to widen it out to this dotted line right here. Okay, great. So see this dotted line. And now if I follow the dotted line all the way down, and let's go back to the ground state, you can see not much tunneling characteristic outside of that border. But what if I go nearly to the top of the well? What if I excite something all the way up there? Look at that. There is definitely a good amount of probability of finding that electron outside of the well. And in part, that's because we've nearly ionized it out of this potential energy well, okay? Which is really cool to think about, how tunneling can play a role in the ionization of something, like literally kicking the electron out of this well, okay? So also what's cool is I can change the depth of this well. So, I do that by grabbing this one. So now that's a 10 electron volt, barrier. So as I make it bigger and bigger, look what happens to my little tailing, the little tunnel tail there at the bottom, right? So as I make that higher and higher and higher, it has a harder time tunneling out of the barrier, which is what we would kind of expect based on our discussion. So now what I want to show you, what's really cool, what's more realistic, electrons don't exist in these little square wells. It's actually a well, like this is actually the Coulomb potential, right? And so what's really neat there, you can see in the ground state, it's predicted to be, the probability density somewhere right there in the middle. But now if you look at this, I've got some bound states up here that get very, very close to being, it looks like they should be tunneling out. They should have some probability out there. But there is such a strong pull from the Coulomb potential in here that it's keeping that electron bound. So in other words, we still have a lot of things to consider in building up our wave functions to describe atoms. We haven't even included the fact that there is a positively charged proton keeping that negatively charged electron sucked in to this potential energy well. So we're going to have to build that in our coming equations. So in the last couple things I want to show you about this figure. So this is really cool. So there's the two-well diagram. So this is a simulation of molecular bonding. So you could think of each one of these wells as a different nuclei, okay? And where you can see really, so now at this ground state, right, they look pretty well separated. But if we start to go up in these higher levels, you can actually see that there's shared probability between the two nuclei, and we're going to explore that in more detail. And what's also really cool in this simulation, here's the mini well simulation, and we'll just do the 1D Coulomb. And this is actually a simulation of metals, right? Of a bunch of metal atoms existing in this mini well, or what we call this banded structure, okay? And so this is also really cool to see how you can change this. We can, oops, I thought I could do more changing the space of the atoms. But as you can see now, the wave functions get really complicated for these figures. So I'd encourage you to play around with this. This thing is really, really cool. Okay, folks, that's it for the lectures on translations. Next, we're going to be moving into talking about vibrations. All right, I'll see you later.